All right, we're going to finish up chapter 12 by looking at example 12:12. So this is a design problem that puts together a lot of what we've talked about so far. So we are told in the problem statement that we have an AISI 1020. That's a type of steel, and we have to use it, a cylindrical shaft, to transmit 50 kilowatts of power. When I work with metric, I like to put everything in the base units, so I'm going to rewrite that 50 kilowatts as 50,000 watts. Now, the thing to know about the steel material is its modulus of rigidity. We're going to need to know that. We can look that up in Appendix G in the back of the book, and we should see there that the modulus of rigidity for AISI 1020 hot rolled steel is 79.3 is the value in the table. But if you look at the top of the table, the units that are given are in megapascals times 10 to the third. So a mega is 10 to the sixth. So this is equal to 79.3 times 10 to the 6th times 10 to the third is 10 to the 9th. 79.3 times 10 to the 9th pascals, which is a Newton per meter squared. Okay, so we've got 79.3 times 10 to the 9th pascals as the modulus of rigidity. 50,000 watts is the power that needs to be transmitted by this shaft. And we're given an allowable shear stress. That's one of our design constraints. The allowable shear stress cannot exceed 67 megapascals. So that's 67 million pascals. The speed that the shaft rotates at is 6 revolutions per second. So N sub r has to be in RPMs, not revolutions per second. So what we need to do is we need to take that 6 revolutions per second and convert it. For every 60 seconds, there is 1 minute. And so 6 times 60 is 360 RPM. That's the unit we need. We're also given an allowable angle of twist. So theta allowable is, and this is per meter length of shaft is the way it's described. So the length is 1 meter, and theta cannot exceed 0.065 radians. We need to determine the required diameter for this shaft. So the first thing to do is to figure out how much torque is going to cause this much power to be transmitted. So I'm going to scroll down here, and let's take a look at our power transmission formula for metric. The number of watts is equal to 2 pi times our speed, revolutions per minute, times the torque divided by 60. So I know that we're kind of like multiplying by 60 here to get it into RPMs, and then dividing by 60 again. We're kind of undoing what we just did, but that way it works with the formula as given. You may realize that, I guess I just don't need to follow that step, and then I can remove that 60 from the formula. If you figured that out, good for you. If not, We just go through the steps of converting to RPMs for use in this formula. So this is going to be equal to 2 pi times 360 times our torque, which is unknown, divided by 60 equals our, our power was 50,000 watts. Let's go back down here. Okay, and this is equal to 50,000 watts. So we want to solve for T. So T is going to be equal to 50,000 watts times 60 divided by 2 pi times 360. And so when we multiply this out, we get 1326 Newton meters. That's the amount of torque that we're applying to this drive shaft. So, how much shear stress is that going to cause? What type of angle of deflection is that going to cause? And how big of a drive shaft do we need so that we don't exceed our design constraints? Let's look at stress first. We have a couple design formulas to use when designing a solid shaft. The first is for stress, and it is d, diameter, equals the cube root of 16t over pi times the allowable shear stress. So this is equal to the cube root of 16 times our torque we just found was 1326 Newton meters. And pi is just pi. And our allowable shear stress, if I peek back up here, was 67 million pascals. 67 million pascals, which is a Newton per meter squared. Okay, so this is going to work out to be 0.0465. Yeah, I'm getting 0.0465. The reason I paused there is because that's different than what it says in my PowerPoint. I think I've got a typo in the PowerPoint. I think I've got these last two numbers, the 5 and the 6, transposed in the PowerPoint, but I believe it should be 0.0465 meters. But if we're going to describe the diameter of a relatively small steel shaft, rather than using this very small decimal, it would make more sense to move this decimal place over 3 places and say that we need a diameter of 46.5 millimeters. Now this is only based on stress. We also need to take into consideration the allowable angle of twist. So our formula for designing a solid steel shaft based on angle of twist, it looks similar, but it is slightly different. D equals the fourth root of 32 TL over pi theta G. So this is equal to 32 times the torque, which was 1326 Newton meters, times the length, which was 1 meter, divided by pi times theta, which is going to be our allowable theta. And remember, this has to be in radians. And we were given 0.065 radians. 0.065 times g. Let's scroll up here to remind ourselves what g was. G was 79.3 times 10 to the 9th. 79.3 times 10 to the 9th. I'm going to take all of this to the power of 1/4. So if you were wondering how do we get a 4th root out of a calculator, I just use a regular scientific calculator. Some of those fancy graphing ones might actually have a 4th root button. I typically just put it all in parentheses and raise it up to the exponent of 1/4. Mathematically, that's the same thing. Okay, so our required diameter is going to equal 0.0402. Again, that's in meters. Millimeters would be a more appropriate unit to describe the size of a steel rod. So this is going to be 40.2 millimeters. And again, I'm realizing that this value is slightly different than what's in the PowerPoint. I think that comes from the fact that G in the appendix changed from the old edition of the book to the new one. So since I'm using a slightly different version of G for the steel, gives me a slightly different answer, 40.2 versus 40.5, but that's really close. We're talking 0.3 millimeters, not that big of a difference. So, based on our two design criteria, stress says we need to have a bar that's 46.5 millimeters. Angle of twist says we need one that's 40.2. So stress is going to control the design. So we need at least a 46.5 millimeter solid steel shaft. I'm not sure if you were to go out and buy one, what types of increments they come in. I'm guessing maybe 5 millimeters, so 5 or 10. So I'd say we could probably round that up for design purposes and use a 50 millimeter diameter steel rod. And that will transmit our 50 kilowatts of power at the specified rate of speed without exceeding the allowable shear stress or the maximum angle of twist.